So today we're going to be talking about transformers. So in essence, a transformer is simply a magnetically coupled circuit that consists of two or more windings or coils. Transformers. So a transformer, excuse me, is a magnetically coupled circuit containing two or more windings or coils coupled by a common magnetic circuit. There we go. So two very common examples of transformers that you guys may see are what are called the core type transformer and the shell type transformer. And so I'll try to draw a quick representation of these. What color have I been using for core material? It's been so long, I don't even remember. Blue. Okay, I'll do it as blue. Okay, fine, whatever. I'm going with blue because it started with blue. One day in the very distant future, these will all just be PowerPoints. All right, so I've got this core, and I would just simply wrap a couple of coils around the core, like so. This guy is going to have N1 turns. It'll have a current I1 of T flowing through it. Then I'm going to put a second coil over here on the right-hand side. I'm going to wrap it in this direction, like so. I'm going to pass a current of I2 of T down it. This coil has N2 turns. Based on the direction of my windings, my flux phi1 of T should be flowing in this direction, and my flux phi2 of T, so that's the flux generated by coil 2, should be flowing around in that direction so that our mutual inductances are positive quantities and they're adding together. So this is a core type transformer. And then the other type that you may very regularly see is what's called a shell type transformer. So let me just draw that one over here. So I'm drawing a cinder block-like shape. And let me throw some windings on this guy. So this is winding 1. I'm just going to put an arrow to indicate the direction of current flow. Here's winding 2, which has N2 turns. I'm going to put an arrow here to indicate the direction of current flow. And then, so here's where my flux, so phi1 might be up in this direction, and phi2 would be down Like so. I literally just drew the coil windings that particular way so that they were opposite, just so that it was easier to fit the information on here. The direction of the windings is completely up to the person who's designing this thing, so it won't always be this way. But anyway, so this is a example of a shell type transformer. Okay. The schematic representation for a two-winding transformer, bless you. So as part of some larger circuit, which is what those ellipses mean, we would simply have some coil having N1 turns, and then over here, a second coil having N2 turns, and here's our terminal to connect elsewhere in our circuit. Okay. So typically speaking, one winding is connected to an AC supply and the other is connected to an electrical load. So I'm going to kind of draw those things in here. I'm going to do them in, I guess, a gray color. So if this is our AC source, and then over on this side is some load impedance ZL, then typically we would call N1 to be our primary winding, and coil 2 over here would be our secondary winding. So whichever side of our transformer is connected to our source, we typically call the primary. Whichever side is connected to our load, we typically call the secondary, okay? Then we have another caveat over here, and I'll write this out specifically. The winding with the higher number of turns is commonly referred to as the excuse me, I forgot the A, high voltage winding, or HV winding. And then the winding with less turns, or the smaller number of turns, let's write it as less turns, is commonly referred to as the low voltage, or LV winding. So I'm mentioning that specifically because so the high voltage winding and the low voltage winding is a fixed thing because one will have more turns than the other, unless you just have a one-to-one isolation transformer, which is definitely a thing, but not something that we're going to really care about too much. So primary versus secondary depends on how things are connected. Low voltage versus high voltage just depends on the arbitrary number of turns in the given coil, okay? So transformers are used in a large variety of applications. Isolation transformers, which I literally just mentioned a moment ago, are used in low power electronics and control systems to isolate circuits and to match the impedance of a source to a load for maximum power transfer. So an isolation transformer system might look something like this, okay? So imagine this is the source side of the system where we have some signal we're trying to process in some way, shape, or form. So this might be something like the output of the pickup from a guitar or something like that. There will be some signal resistance associated with this source. So we're dealing with a practical voltage source. So this is the source side of my system. And then we'll connect our source to some type of amplifier. And our amplifier is typically characterized by some input resistance. And I'm going to call this voltage Vx as a function of time. And then over here on the right-hand side, I'm going to have what is essentially the output portion of the amplifier circuit. So this is some current gain factor multiplied by our input voltage Vx. Here is our output resistance. So everything between this set of terminals is a simplified representation of an amplifier circuit. And I'm going to put some dashed red lines here to delineate the different effective stages of this system. And then connected to the output of the amplifier circuit might be an impedance transformer. Which I am drawing as an ideal transformer. Talked about these a little bit in, was it 280 last spring? And then lastly over here, we might have our load, which in this example of a guitar amplifier system would represent a speaker. Okay. So in a system like this, our transformer is effectively playing double duty here in as much as it is isolating the load from the amplifier. And so the reason why we might need to do that very specifically is because the impedance of a speaker, how many of you guys dabble in being a musician or anything like that? Anybody here play electric guitar, even if it's shittily? You have any idea of, for what it's worth, I play electric guitar rather shittily. Anybody have any idea of what the impedance of a speaker in an amplifier cabinet might be? So 4 ohms, 8 ohms, 16 ohms are typical values, right? So pretty darn low, right? So depending on, like if you have a single, let's say a 12-inch speaker or something like that, its impedance is probably 16 ohms. You have 2 speakers in a cabinet, the overall impedance is probably 8 ohms because it's those 2 16 ohm speakers connected in parallel. If you have a 4x12 cabinet, it might be 4 ohms, it might be 8 ohms, it might be 16 ohms. It just depends on how it's wired. But typically speaking, the impedance of a speaker is very, very small. Single digit to tens of ohms kind of thing. Now, there's no way for you guys to particularly know this because you don't have a particularly rigorous, or to my knowledge, any background in power electronics or anything like that. But typically speaking, the output resistance of a transistor-based amplifier, so a solid-state amplifier, is going to be fairly large. So hundreds to thousands of ohms. And so if those two things are directly connected together, we have an issue because something large in parallel with something small is going to look like effectively something small. And so practically no power is actually getting delivered to the speaker. So instead, we have that transformer, which is providing isolation between those two things. And the turns ratio also allows that low impedance speaker to potentially look like a much larger impedance. And we'll go through the math behind that here shortly. So this is a common everyday practice of using a transformer. Every one of you guys has a transformer like this in your car stereo system, things like that, okay? So this is something that we all see on a day-to-day basis, whether or not we realize it or not, okay? So this is just a simple example of where we might have an isolation transformer. Instrument transformers are used to measure voltages and currents in AC systems. So some of you guys that have had internship experience with electric utilities and stuff like that might have heard the terms like a CT and VT tossed around. That stands for current transformer and voltage transformer. You might have also heard of PT for potential transformer or power transformer. All of those type of things are instrument transformers that are effectively just used to measure current and voltages in system as part of a larger control system to make sure that, hey, we aren't seeing any surges, none of our equipment is going down or is going to be exposed to signals that are higher than their rated values and stuff like that, okay? So that's instrument transformers. Then we have power and distribution transformers. So I'm going to draw a little depiction here. So this is a small example of an AC distribution system. The only difference really between a power and a distribution transformer is literally what they are rated for, okay? So the size of the windings, like the size of the wire in the windings is going to change because some of them have to be able to handle a larger current and stuff like that, but largely they're effectively the same thing. It's just for different parts of a similar application. So in a very simplified AC distribution system, we might have something like this, where we've got an AC generator. So realistically, this is just a turbine somewhere. Could be steam powered, but how that steam is generated might be burning of coal, burning of liquid natural gas, might be just heat generated from something else, like one of those processes. There's a current thing that Entergy is doing. It's called effectively hybrid generators, to where they burn liquid natural gas to generate steam, but also the excess heat is also used to generate steam, so that they're effectively doing some energy harvesting to increase the output of their system. So anyway, just basic AC generator of some sort. A typical generation level might be somewhere in the ballpark of 30 kilovolts RMS. So I'm going to put that over here as plus minus 30 kV RMS. And then connected to the generation side of things will be, typically speaking, a step up power transformer. So that on the secondary side of this power transformer, our voltage might be stepped up to somewhere approaching 500 kilovolts RMS. Typically speaking, when electricity is transmitted over very long distances, we step it up to incredibly high voltages because the higher the voltage we transform it to, the smaller the current is, which means we deal with less I squared R or ohmic losses, which means our system is running effectively more efficiently. So it's more cost effective to transmit power over very long distances if you step it up to really high voltages. It's not until it literally comes into your home that it is no longer on a kilovolt size voltage, which we'll get to in here in a moment. So just for what it's worth, over here we have the generation side. And then now we're in the transmission side of things. Running out of space there, but you'll get it. Then we'd probably run this into yet another transformer, but this guy is going to be a step down. So this would be like an industrial voltage level. So maybe something in the ballpark of 44 kilovolts RMS, right? Everything beyond that 500 kV is what we're going to consider the distribution side. So 44 kilovolt RMS consumer is going to be some sort of very large scale manufacturing plant, like probably like a metal foundry or something like that, where they need a whole hell of a lot of voltage and potentially current to melt slag and things like that. For a smaller scale manufacturing thing, this might get stepped down to, say, 4.5 to 5 kV, or it might be in a residential area, which I think around here, like if we looked at the 13.5 kV, I believe, but some, tens of kilovolts, single digit kilovolts, tens of kilovolts kind of range. So let's call this 13.5 kilovolts RMS. And then finally, we would get down to our home. And so in homes here in the States, I'm kind of running out of room here, we actually get 240 volts RMS. And then that output 240 volts RMS, let me just write home here. That's actually, the secondary winding of that transformer is typically a center tapped transformer, which gives us access to plus and minus 120 volts, which added together looks like 240. So we have two 120 volt access voltages in our homes that are 180 degrees out of phase with each other. That's used for all of our simple consumer electronics and things like that. Our larger appliances like our ovens, water heaters, things like that require the full 240. For those of you with electric vehicles, a level 1 charger uses a 120 volt circuit. A level 2 charger uses a 240 volt circuit, etc. And then to make it potentially more confusing, if you live in an apartment complex, instead of having 240, you probably have 208. So that would be a 3-phase thing where you would have a 208 and delta configuration, which looks like 120 in a, so that 208 line to line is the same as 120 line to neutral, effectively, which we talked about 3-phase power a bit back in 280, and we'll revisit it here. So as a side note, most modern appliances are designed, or higher voltages appliances are designed to work at both 240 volts RMS or 208 volts RMS, so that they don't have to make a completely separate unit for apartment buildings and stuff like that. Anyway, this is an example of where power and distribution transformers are used, okay? So isolation transformers, instrument transformers, and then power and distribution transformers are the majority of the transformers that you will see depending on where you go out to work, and they're all generally based on the same principles. And so now we're going to talk about that. So as a quick review, let's look at the concept of ideal transformers. So I'm going to draw a simple circuit here. And I'm going to draw out the transformer as a physical structure instead of a circuit element for right now. So here is my core. Relish the fact that I'm still drawing pictures and not just murdering you all with math yet.
Yes, Bob.
So here's my first coil having N1 turns. Over on the other side, I'll have the secondary coil having N2 turns. So I'm going to label a couple of things here. So let me start by drawing some source. Okay. So this is my source voltage, and we're going to be working in the RMS phasor domain so that we're dealing with just RMS voltages and currents and all of that kind of good stuff. So that's my source voltage. Okay. So let's talk about a couple of quick things here. So across these terminals, I'm going to have some voltage V1. And this is what is commonly referred to as my primary voltage. So I'm going to make a quick note of that. And then I'm going to draw a current here that I'm going to call I1. And this is my primary current. So that, hopefully very obviously, everything with a 1 subscript is a primary side of the transformer quantity, okay? Now, something that we didn't necessarily talk about much, if at all, and I say that because I genuinely don't remember what we talked about in 280, I'm going to put a voltage here, and I'm going to call it E1. So this E1, the E effectively stands for EMF or electromotive force. Voltages are an example of an EMF. So we should really think about this voltage E1 as the voltage that is induced across the terminals of, induced across the coil, which is not necessarily going to be the exact same thing as the voltage across the terminals of the coil. The reason being is that if our coil is lossy or has some finite resistance, we should see some small difference in those two voltages, okay? So E1 is the induced voltage, V1 is the terminal voltages, okay? And then we'll have, goodness, I didn't mean to do that, a similar set of voltages and currents on the secondary side, right? So here's my terminal voltage, V2, which is my secondary voltage. Here is my secondary current, I2. And then I will have an induced voltage, E2, across my coil as well. And now I'm going to connect a load network, which is going to contain just a switch connected to some load impedance ZL like so. So this is just a simplified representation of a circuit containing a transformer, okay? So the transformer can be considered ideal if it has the following properties. First one, the resistances of the windings are negligible, meaning effectively that they're so small we consider them to be zero, okay? Criterion 2 is that all fluxes are confined to the core and link both windings. In other words, our core losses are negligible. So if I draw my flux path for this guy, or it would look something like this, where everything is nice and confined interior to the core material. This is our flux as a function of time. Okay. So nothing is leaking. And then lastly, core permeability is infinite, meaning that mu c is approaching infinity. Okay. So those are our three different criterion for an ideal transformer. And rather obviously, no practical transformer will ever be an ideal transformer because real transformers have resistance in the winding. We can't constrict all of the magnetic flux to be inside the core material, meaning we have losses, and all real materials have some finite permeability. So we can get close to ideal transformers, things that are operating at 99+% efficiency, but we can never really truly hit this, okay? All right, so working under this simplified constraint of having an ideal transformer, let's look at a couple of things, okay? So with our switch open, a time varying voltage Vs of t connected to the primary windings will establish a time varying flux phi of t in the core. A voltage E1 of t will be induced in the winding, in the primary winding to be specific, such that, so we have our source voltage Vs of t is going to be the same voltage as our primary voltage V1 of t because our source is connected directly across the terminals of our primary winding. And for a ideal transformer, this is the same thing as our induced voltage E1 of t, which is simply the number of turns in the primary coil N1 times the derivative of our time varying flux with respect to time. And we could rearrange this relationship to find that V1 of t divided by the number of turns N1 is simply the rate at which the flux changes.
After a voltage. It's E1?
E1 as a function of time. Let me write that better. Lowercase e1. Okay. Core flux passes through the secondary windings. And induces a voltage E2. So E2 of t will be N2 times the derivative of our flux with respect to time. And because this is a lossless transformer or an ideal transformer, E2 is the exact same thing as V2. And we can rearrange this relationship to find that V2 as a function of time over N2 is also equal to the change in flux with respect to time. So putting these relationships together, we wind up seeing that V1 over N1 is equal to V2 over N2, which could be rearranged as so here's where I want to take a quick moment here. Okay. So I believe in 280, I defined the turns ratio of a transformer as number of turns in the secondary divided by the number of turns in the primary. I'm going to do that here as well. So I'm going to say that V2 over V1 is equal to N2 over N1, and we're going to call this A, which is the turns ratio. The reason why I hesitated there is because for whatever reason, that is the turns ratio that is typically given in circuit analysis textbooks. And that's a dog. In most textbooks related to electrical machinery and power systems, the turns ratio is very typically given as the ratio of the primary the turns ratio over the secondary turns ratio. Okay. I don't know why there is this disconnection between the different sides of using this. But like I said, just typical basic circuit analysis textbooks dealing with transformers and magnetic circuits define it this way. This is the way that I defined it when I taught 280. So this is the way that I'm going to do it. But you may see it expressed as N1 over N2, which is really just the inverse of what we are dealing with. So it can get a little bit confusing depending on which references you're looking at if they're using the opposite convention that you are. So I just want to make you aware of that. Okay. All right. So with the switch closed, a current I2 will flow in the secondary winding, providing a magnetomotive force, MMF, 2 of N2 I2 of T for the core. This MMF is opposite to MMF1 of the primary winding. And just to clarify that statement, the reason why I'm considering those two MMFs to be opposite is because I have defined the current I1 as flowing into the coil or into coil 1, and I've defined I2 as flowing out of the secondary coil. So that's why I'm saying that those two MMFs have opposite signs. Okay. So one's flowing in, the other one's flowing out. So the MMF should be opposite to each other. So anyway, such that we can say that the net MMF is equal to N1 I1 minus N2 I2 is, as somebody mentioned, 0, implying then that N1 I1 must equal to N2 I2, and therefore the ratio of I2 to I1 is N1 over N2 is 1 over our turns ratio. Lastly here, dealing with specifically an ideal transformer, the instantaneous power absorbed by the primary winding is, I'm going to call this P1 of T, is simply V1 times I1. The instantaneous power supplied by the secondary winding is P2 of T is equal to V2 I2, and since we have an ideal, read that as lossless transformer, P1 of t, which is V1 times I1, must equal P2 of t, which is V2 times I2. Right? So effectively, the amount of power that our primary winding absorbs has to be the exact same amount, the amount of power that our primary winding absorbs from our source has to be the exact same amount as our secondary winding delivers or supplies to our load. Power in has to equal power out because of the law of conservation of energy, right? So this means that as voltage V1 increases, so if I said that incorrectly. So if V2 is larger than V1, then I2 has to be smaller than I1 to make those products constant, right? So if we step up the voltage with a transformer, we alternatively also step down the current and vice versa. Okay. So sorry, my nose is itching so much. So let's talk about impedance transforms really quickly. Okay, I think we talked about this in 280. I just want to remind you of this because we're going to wind up using it pretty regularly as we go through things. And it's easiest to understand dealing with an ideal transformer. So let's say that I have the following simple AC circuit, okay? So I've got some kind of excitation source on connected to the primary windings of my transformer. So this is going to be my voltage V1. I'm defining everything, dots are on the same side and all that kind of good stuff so that we don't have to worry about literally any of that gobbledygook in this class. I've got some impedance that I'm calling Z2 because it's connected to the secondary side of the transformer. Here is my secondary voltage V2. I'm defining my primary current as flowing in, my secondary current as flowing out, like so. Okay, so by definition, my impedance Z2 is simply the ratio of my voltage V2 to my current I2, right? Because impedance is nothing more than the ratio of phasor voltages. Okay. So if I wanted to find the impedance seen looking into my primary windings. So I'm gonna say that if I look into those terminals and I try to find my input impedance Zn, that impedance Zn would, by definition, simply be equal to V1 over I1. But let's look up here really quickly, right? So instead of this V2 as a function of time and this V1 as a function of time, let's consider that we're looking at the RMS phasor equivalents of these voltages. So we have a relationship that V2 over V1 is equal to A. I'm just going to tuck that in over here, kind of as an aside thing, right? So V2 over V1 is equal to A. We could alternatively express that as V2 is just equal to A times V1, or V1 is equal to V2 over A. Do we agree with the algebraic manipulation of those simple relationships? Let's start there.
Cool.
Okay. For our currents, we'll get to that in a second. We have I2 over I1 is equal to 1 over A, which I could algebraically manipulate to say that I2 is equal to I1 over A, or alternatively, I1 is equal to A times I2. Are we okay with how I've algebraically manipulated that? So for an ideal transformer, I can express V1 in terms of V2, which is going to look like simply V2 divided by A. I can express I1 in terms of I2, which is just A times I2. And now that V2 over A effectively puts an A in the denominator. So I would have 1 over A squared multiplied by the ratio of V2 over I2, or 1 over A squared times Z2. So that is the impedance seen looking in. So this is the reflected impedance, which we typically denote as Z2 prime. So if I want to refer an impedance, generally speaking, if I want to refer an impedance from the secondary side of the transformer to the primary side of the transformer, I divide by a factor of A squared. I'm going to write that down underneath here. So generally speaking, if we want to refer, and I'm also going to put here slash reflect because that is a common term also used. Connected on the secondary side of the transformer to the primary side. We divide by A squared. So what do you think we would do if we wanted to refer an impedance connected to the primary side over to the secondary? Yeah, literally it. Multiply by A squared instead. So that, generally speaking, is our rule for sending impedances from one side of the transformer to the other. I'm making a specific note of that because that is a technique that we are going to use rather often in building the different equivalent circuit models that we're going to be dealing with. So let's get around to that. I'm going to do this as kind of a separate section. Okay. So let's talk about this here as the practical. Did I go too fast and you guys missed stuff? Did I switch pages too quickly? Okay. Practical transformer model. Okay. So for a practical transformer, all of the assumptions that we made about an ideal transformer are no longer valid, meaning that we are going to have some wire or winding resistance. We are going to have some core losses, and the permeability of our core is not infinite. So in order to account for these non-idealities, we have to update our model, okay? So I'm going to now draw another simple portion of a circuit containing a transformer. And I'm going to try to include some of these effects, and then we're going to talk our way through what our practical model is going to look like, okay? So for the most part, it's going to look pretty darn similar to what we just did. Here's our primary winding having N1 turns. Here's our primary voltage V1. Here's our primary current I1 like so. Over here, I'm going to have our secondary winding having N2 turns. Here's our secondary voltage V2, our secondary current I2. And now when I draw my flux, so I've got some flux circulating around, confined to the core, but I might also see some flux leakage. Like so, okay? So let's start kind of talking our way through this thing, okay? So I'm just going to give myself a set of terminals over here on the left-hand side of the screen, and I'm going to give myself a set of terminals over here on the right-hand side of the screen. And we are literally just going to talk our way through things, and then I'll probably make some annotations, okay? So these are the primary side terminals where we would see our voltage V1. These are our secondary side terminals where we would see our voltage V2. All right. So if I look at my pictorial diagram here, and I'm kind of following my path, what's the first thing that I see? Well, it's my coil 1 having N1 turns, okay? So in a practical transformer, this coil has some finite amount of resistance because it's made of a real wire that has resistance, okay? So I'm going to include a resistance here that I'm going to call RP, for the primary winding resistance. And very similarly, on the secondary side, that coil is also made of real wire. So we'll have, crap, I drew that in the wrong place. Let me fix that. some resistance RS. So these resistances RP and RS are there to account for what are called the copper losses or I squared R losses that we might see. So essentially, as we pass current through a wire, it tends to heat up, and some of the energy that we're trying to transmit or some of the power that we're trying to transmit is lost because it's converted into heat. That's what these guys are doing, okay? Now, because we have coils, we are also going to have effectively some inductance. These inductances represent the flux losses, okay, in our system. So because it's flux losses, we're not actually losing any energy per se. So we need an energy, an element that doesn't have a resistive amount of loss. So I'm going to put an inductance here that I'm going to call JXP. So this is taking into account our flux leakage in coil 1. And I'm going to put an inductance here that I'm going to call JXS that is accounting for our flux leakage in coil 2. Okay. So these are what are called our series components. Okay, so we have copper losses accounted with by resistances RP and RS, and we have flux leakage in coils 1 and 2 that are accounted for in our inductances, XP and XS. Those inductive reactances, XP and XS. Okay. So now let's talk about some other losses. Okay. So we are going to have power losses in our core because the process of magnetizing our core material induces eddy currents, which you guys watched in one of my previous videos. And those eddy currents cause the core material to heat up, right? So I'm going to choose to represent that as some resistance here that I'm going to call R sub C, okay? This resistance is placed in parallel or in shunt across the terminals of our winding because the value of these losses is dependent on the amount of applied voltage, okay? So it needs to be in parallel so that it takes into account that total voltage. The next component that we're going to talk about represents the magnetizing current needed to actually magnetize the core. Now, we're choosing to give this an inductance. So I'm just going to go ahead and put that in right here. I'm going to write it as JXM, where the subscript M is for magnetization. And the reason why we're treating this as an inductance is literally because we can see that the current that happens when we magnetize our core lags our voltage by 90 degrees, which is exactly what this describes, or that's the phase relationship in an inductor is the current lags the voltage by 90 degrees. Okay. So the last thing that we need to add to our model is the fact that in a transformer, we can step up and step down voltages. So the last component in our practical transformer model is actually an ideal transformer, which I'm going to put over here. Here's N1, N2, my lines. And here's my dots. So this is our practical transformer model. Okay. I'm going to redraw it. Actually, I'm not going to redraw it. We'll talk about it in just a second here. I'm going to wind up redrawing it, but I'm not going to do it yet. So this is a kind of big and ugly thing, right? There's a lot of stuff going on here, in as much as we've got some elements connected in series, some connected in parallel, some are on the primary side of the transformer, some are on the secondary side of the transformer. We actually have a damn transformer in this thing, which can, in and of itself, excuse me, be a little bit confusing. So one of the ways that we can simplify this model is by referring all of our impedances from the secondary side to the primary side, or vice versa, all of our impedances from the primary side to the secondary side. So I'm going to choose to refer my secondary impedances, these guys right here, over to the primary side of my transformer. So referring RS and JXS to the primary side yields the following circuit. So here's my terminal. Here's my terminal. This is my voltage V1. Here's RP JXP, like so. I'm going to draw those parallel things slightly differently. This is how you usually see it in textbooks and stuff like that. And then over here, make sure I have enough room. I'm going to put my reflected resistance. So this is going to be RS over A squared. This is going to be JXS.
Squiggly line between J, X, and R. That's just an R.
Yes. And then here's where the terminals of my ideal transformer are. And for what it's worth, how did I draw? I didn't draw my current, so I'll put them here. So here's my secondary current, I2. Here's my primary current, I1. Okay, so we're going to break this thing down into a couple of, not necessarily smaller parts per se, but I'm going to add a little bit more context to things here. Okay. Thank you, Brock. Yes, it is. So I'll go ahead and note that the transformer is still ideal. Okay, so we've got this representation. Just for what it's worth, I'm gonna put some notes up here. So we typically call this RS prime, and this guy up here is XS prime, where that prime designation literally just means we referred it to the primary side. If you ever see me use a double prime or two slash marks, that means we're referring things over to the secondary. We'll get to that here in a moment, okay? So now we have everything over here referred to the primary side. I want to make a note of a couple of different other currents that we might see in this system. So I'm going to, excuse me, add some of the kind of annotations here in blue. So this current right here that I'm labeling I sub E is what's known as the excitation current, okay? So the excitation current is a current that is added to the primary current. So if we're looking at this from a Kirchhoff's current law perspective, we have the excitation current and the primary current combined together to establish a flux around our system, okay? Then we're going to have a current here, IC, that is our core loss portion of the excitation current. So this is the portion of that current that is responsible for having the core heat up, giving us those associated losses. And then over here, we have what's called a magnetization current. So this is the portion of the excitation current that is used to magnetize the core, okay? Excitation current. Excitation. So IE is the excitation current, which is effectively what we need to have. Our transformer needs to be excited or energized in order for it to work, essentially. Then we have our core current, which is the portion that's responsible for our core losses. And then we have our magnetization current, which is the portion that's responsible for magnetizing our core. Okay. Now, let's look over here really quickly. I'm going to do these guys kind of in purple, okay? So this current right here, I'm going to call I2 prime. And it is the secondary current referred over to the primary side, okay? So it's not I1 per se, because we have a practical transformer, but it's going to be something similar to I1 because it's the current on the primary side. We're just calling that voltage V1 connected to those left-hand terminals our primary voltage. That current I1 that's flowing into those terminals our primary thing. So anyway, so this guy right here is just A times I2. And additionally, we're going to have a voltage here, V2 prime, that is just V2 over A. Now, the reason why I am making a note of those particular quantities is because if we understand what that current there is and what that voltage is, if we had some sort of load, I'll draw it in gray right here. ZL, and we referred this load also over to the primary side of that ideal transformer, there's no need for us to even have the transformer in our model anymore. So like realistically, we would have all of the exact same information with the following circuit. Let me, this less shittily, my apologies. So we now have a model for our transformer and the connected load that literally no longer needs to have a transformer in it at all. This is very simple AC circuit analysis at this point, which is why this is such a powerful model, right? If we just take into account the impedance transformations, the voltage transformations, and the current transformations when we're drawing our system, the information supplied by the transformer is completely redundant. Effectively, there's nothing connected to the secondary side anymore. So why does it even need to be there, is the argument that I'm making. Okay. So this is the first simplified model that we are going to be dealing with in this class. This is commonly referred to as the T equivalent circuit for a transformer. So let me just make a quick note of that. I'm just going to put a dashed line across here, and everything over here is the T equivalent circuit, including the fact that our voltage on the secondary side there is V2 over A, and our current on the secondary side over there is A times I2. Okay. So we can actually simplify this thing a little bit further if we wanted to. Okay. So our next simplification is going to be what is commonly referred to as the cantilever equivalent circuit. You'll see why we call it that in a moment. So this simplification happens or can be used because we can make an observation about something, okay? So in transformers where we have effectively a constant steady state sinusoidal voltage and we're operating at a fixed frequency. So this would be effectively every transformer in a power transmission or distribution system. The magnitude of the excitation current is very, very small compared to the rated winding current, meaning that our current IE, if I draw it in here really quickly, is really only, 2 to 5% of I1, okay? Essentially meaning that almost none of I1 branches off and flows down through this excitation current. Almost all of I1 continues flowing through those reflected impedances. So what we can do is we can literally just lump together all of those series components and only be introducing a small amount of error into our system since we know almost none of it actually branches off. So our cantilever equivalent circuit would look something like this. So here's V1. Here's I1. I'm going to draw my parallel or shunt components here. So here's RC, JXM, and then here's a resistance that is RP plus RS over A squared. Here is a inductance that is J XP plus XS over A squared. And then here is our effectively referred secondary terminals. So this voltage right here is V2 over A. This current right here is A times I2. And for what it's worth, this is still our excitation current, IC, and IM. Okay. Excuse me. We might lump these things together and call them the equivalent primary resistance. Goodness. And we might lump these together and call them the equivalent primary reactance, which is what that P subscript stands for. We could, if we were so inclined, so this is one cantilever equivalent circuit. We'll call this the primary referred cantilever equivalent circuit because everything is literally referred to the primary side of the circuit. Or we could do a secondary referred cantilever equivalent circuit, which would look something like this. I swear to God, I'm almost done boring you guys for today.
I feel like you go for a little bit longer.
So here's AV1. This is our current that is I1 over A. So I'm going to refer this shunt branch over to the secondary side. So this is going to look like A squared RC. This is going to look like J A squared XM. This is my resistance. So RS is going to be left alone. I'm referring RP over. So that's going to look like A squared RP plus RS. This is going to be J A squared XS. This is going to be XP plus XS. This is just the real value of V2. And this is the real value of I2. So this will be our secondary referred cantilever equivalent circuit. And for what it's worth, we would probably lump these together and call them REQS and this together as XEQS. All right, so let's look at a quick example. And then we'll wrap things up for today. We've only got 15-ish minutes anyway. Actually, let's stop here. We'll work the example starting class on Thursday.